All right, let's say, hypothetically, you wanted to do some basic arithmetic, but you didn't want to just add two numbers together. You wanted to become a cool kid, essentially. Well, you've come to the right place. So let's evaluate 2 plus 6. Easy, right? Wrong. What we're gonna do is we're gonna do something that would make this little simple, I guess, expression into something more complex, but still get the same answer, of course. And what is that answer, you might ask? That is something that we're going to answer soon enough. So let's convert this into a more usable expression. So we know that 2 times 2 divided by 2 is just 2, so we can just do 2 squared over 2, which is still equal to 2, and then we can do 3 times 2, because 3 times 2 is equal to 6. So we have this equation here. Expression, I guess. So let's make x equal to 2, so we'd have x squared over 2 plus 3x is equal to question mark, I guess. So let's convert this even more. Oh my gosh, why I keep writing n? I don't know why. X. All right, so we're going to convert this into a definite integral, because why not? So we know that the antiderivative of x is just x squared over 2, so we can just convert that back into x. We know the antiderivative of x to the 0th power is just x, so we can just do x plus 3, which is equivalent to f of x, because that's our function here. We've converted the antiderivatives back into just regular variables, I guess. So now we're ready for this, I guess, next step here. So we can convert this into integral notation, or definite integral notation. We have our indices 2 and 0, which comes from these two numbers right here. They're just being copied over. So we're gonna have our function here, x plus 3, and we're gonna figure out what this is gonna be. So this brings us to our next step. We have our definite integral here, 2, 0, x plus 3, and we know that, according to a bunch of random resources on the internet, we can equate this integral notation here to the Riemann sum, which is that. Okay, cool. So we of course need to figure out a bunch of values that would fit in. So we know that delta x is equal to b minus a over n, and then we can just convert that into, or plug in these values here. So it's 2 minus 0 over n, which is just 2 over n, and we know that ith index of x is just delta x times I, which is just 2I over n. All right. So now we have our values that we're going to plug into this new function here. So we're going to equate integral x plus 3 is equal to n I equals 1. I'm going to do f of 2I over n. And then we're going to multiply this by delta x, which is just 2 over n. So then we can do a little bit of expanding out, I guess. That's just 2I over n plus 3 times 2 over n. And then we can multiply these two things together to then get 4I plus 6 over n, and then it's squared. Yep, that looks right. Oh, I forgot to write the summation for some reason. So this is gonna look a little less elegant, but it's fine. So then we know that this can be split up into two different summations. And I equals 1, and then we have 4I over n squared plus n I equals 1, 6 over n. Cool. All right, so now we can use a few more summation rules to make it a little more simple. Bear with me here. This might take a second to write. All right, so now we can just use another rule, convert this into whatever n, because n times, I guess, summation with n, and then just a constant, you could just do 6 times n, and then that's just the summation of that. Okay, it's just basic multiplication. N times 6, 6n, and then we multiply this. These cancel out, which gets us to 6. Now we want to calculate this little value here. I don't know why I wrote n squared here, but I'm just going to do I is equal to 1 because yes. And to keep it consistent, of course, and then we don't change the problem. All right, so now we have these values here. We can just use a rule. N plus 1, 2, 4 times n squared. All right, we have this beautiful, I don't know why I wrote this thing here, but we have this beautiful little expression here. We've gotten rid of all the summations and all the integral stuff. And now let's just evaluate this and see what we get. So we know we have 4n, n plus 1, 2n squared plus 6, and we're going to add these together. So we're going to multiply 6 by 2n squared over 2n squared, which is just 1, but we want to make them add up. So we distribute this 4n times 4n plus, or times n plus 1, so we get 4n squared plus 4n over 2n squared plus 12n squared over 2n squared. And then we know we're going to get 16n squared plus 4n over 2n squared. So to get this final sum, all we have to do is get the two highest degree terms on the numerator and the denominator, and then just divide them. In this case, it's 16 and 2. So all we have to do is, I guess I'll just move this right over here. So it's just 16 over 2, and then that equals to 8. So I guess to prove it, we have 2 plus 6, that's equal to 8, of course. And then we used a bit of calculus to then overcomplicate the process and then still get the same answer. We just use a few rules here and there, use the Riemann sum, use a bit of summation rules, and calculated the area of this curve here. Or not really a curve, it's a linear equation. But further proving it, you can just convert this into this and then just go back here and then realize that, oh wait, these are all the same thing. This notation here is basically equal to 2 squared over 2 plus 3 times 2, and that's getting subtracted by 0 squared over 2 plus 3 times 0, because we're just plugging in these values into here and then subtracting them. And this, of course, becomes 0 because anything multiplied by 0 is 0. So we have 0, and then we evaluate this expression here. We have 8 minus 0, and that still gets us 8. So that, my friends, is a really stupid but satisfying way to solve really basic arithmetic if you don't want to be one of those normies.